Before 2017, the most effective sequence models relied on recurrent layers, architectures that process language through a strict lockstep bottleneck. This forced an O of n sequential constraint. To compute position 50, the model had to wait for the completed computation of the previous 49 tokens. This sequential requirement prevents parallel training and limits the network's ability to model dependencies across long distances. The transformer architecture proposed a total departure from this tradition, the complete removal of recurrence and convolution in favor of attention. By replacing loops with attention, the sequential work drops from O of n to a constant O of 1. To understand how this works, we will trace the end-to-end tensor data flow, following an input sequence from raw embeddings to its final output probabilities. This shift to parallel attention provided the computational efficiency required to scale sequence models to their current dimensions. The process begins by mapping a raw input sequence into learned vectors of dimension D model, which the paper sets at 512. Because the attention mechanism processes every position simultaneously, the engine itself has no built-in concept of word order. Without manual intervention, a sentence like "the cat sat" and its permutation, "sat cat the," would look identical to the model. To begin the injection of order, the raw embedding vector is scaled up by the square root of D model. A fixed sinusoidal positional encoin is then added directly to the vector, providing a signal the model uses to distinguish a token's location in the sequence. These entry mechanics are the mandatory scaffolding that allows a parallel engine to maintain a mathematical sense of sequence. This brings us to the core of the architecture, scaled dot product attention. Each token position generates 3 learned linear projections, a query, a key, and a value. The model determines relationships by computing the dot product between every query and every key, yielding a matrix of raw compatibility scores. These scores pass through a softmax function to normalize them into a set of weights that sum to 1. These weights are then multiplied by the value matrix, resulting in a contextualized weighted average for each position. However, implementing this math naively, without the scaling factor, leads to model failure. As the key dimension dk grows, the variance of the dot products increases. This chart shows how an unscaled distribution collapses into a single massive spike. When the softmax function encounters these large magnitudes, it saturates into a near one-hot factor. This saturation causes the gradients to vanish, effectively stopping the neural network from learning. The paper solves this by dividing the dot products by the square root of dk. This keeps the variance near 1 and the softmax distribution diffuse. Scaling by root d squared is a structural requirement that prevents the model from collapsing during training. To further improve performance, the paper implements multi-head attention. The 512-dimensional stream is split into 8 parallel heads, each with a dimension of 64. While conceptualized as 8 separate heads, it does not require 8 separate hardware modules. This parallelization is achieved through simple tensor misheap and transpose operations on a single matrix. This allows the network to simultaneously attend to different representational subspaces, for example, tracking syntax in one head and core reference in another. Tensor reshaping provides these multiple perspectives without increasing the computational cost beyond that of a single full-sized head. These attention engines are wired into a dual tower architecture. The encoder stack consists of 6 layers that use unrestricted self-attention and feed forward networks to contextualize the entire source sequence. The decoder stack is different. To generate text one word at a time, it must be prevented from peaking at future tokens. This is achieved through masked self-attention, where future pre-softmax logits are set to negative infinity. Masking must be applied to the pre-softmax scores. Zeroing the weights after the softmax will not produce the exact 0 required for causality. The decoder then uses cross-attention, querying the decoder's state while pulling keys and values from the contextualized output of the encoder. This strict negative infinity mask is the mathematical constraint that keeps a parallel engine causal during text generation. In the final step, the decoder's output vector is projected into a probability distribution across the entire vocabulary. To optimize the model, the linear projection weights at this output head are tied to the input embedding matrix. Replicating the paper's results also requires a specific training recipe, particularly for the learning rate. The Atom optimizer follows a strict schedule. a linear ramp for 4,000 warm-up steps, followed by an inverse square root decay. The recipe also includes label smoothing at an epsilon of 0.1, which improves final accuracy, even though it intentionally raises the model's perplexity. Failing to implement these specific parameters will result in a model that performs significantly below its state-of-the-art potential. By entirely removing the sequential constraint of recurrence, the transformer architecture enabled massive parallelization in sequence modeling. This achieved a new state-of-the-art result of 28.4 BLEU on English to German translation, while using only a fraction of previous training budgets. However, there is a mathematical cost. Self-attention requires O of n squared total complexity per layer. As the input sequence grows longer, this quadratic cost becomes the primary computational bottleneck. This quadratic limit is the focus of modern efficiency research, leading to developments like flash attention that aim to optimize these specific tensor operations. The engine of this model consists of scaled dot product attention and multi-head reshaping. Every other component, from layer norms to residuals, is designed to support and route tensors through that core engine. Mastering these specific tensor mechanics is the prerequisite for implementing and optimizing the attention models that have come to define modern sequence transduction.